We have come some way now in our course on tensor analysis. I hope by now I have been able to convince you that rather than think of tensors as a huge bunch of components which transform under coordinate transformation in a rather non-trivial and complicated manner, it is better to think of tensors as cute little machines which eat up covectors and vectors and churn out numbers. Eat up may not really sound very cute. It does have some cannibalistic connotations. So perhaps using the more formal take covectors and vectors as inputs and produce real numbers as output could be a better way to put it. But a tensor can also be seen in other avatars. Instead of being looked upon as a machine which, say, takes in two vectors and produces a number, you can also see that as a machine which takes in a vector and produces a vector. In fact, it is this particular aspect of tensors which is responsible for physics using tensors for many different applications. We are going to explore a few of these from Newtonian physics in this lecture. In the next one, we are going to talk about special relativity, and then we are going to go on to talk about general relativity in later lectures. In the last lecture, we saw that rather than thinking about a tensor as a bunch of n to the power p plus q components, t I1, I2, all the way up to IP, then J1, J2, JQ, so n to the p plus q components in all, which transformed in a particular manner under coordinate transformation, it is actually better to think of them as something else. Okay, let me just write down this first. This is the traditional way of thinking about tensors, at least what used to be the traditional way among physicists, that tensors are things which transform in a particular manner but today we think of them as rather in terms of these machines or multilinear maps which take in p covectors and q vectors and produce a result which is a real number, but more importantly, it produces a real number in a multilinear fashion. That is, if you were to keep all the inputs the same, but replace any one of them, let's say Vi, by some linear combination alpha AI plus beta Bi, then the resulting number will be a linear combination of the two results that will be produced if you were to put in AI alone or Bi alone, weighted by the factors alpha and beta. And that goes not only for the ith vector, it goes for each of the covectors and each of the vectors. So basically all that a tensor is just this. It's a multilinear map from a bunch of covectors and vectors to numbers. Now, as we have seen in the last lecture, you can actually figure out what the components of a tensor, these numbers here, would be starting from this definition as a multilinear map. All you have to do is just feed in the basis vectors for the covectors and vectors, the I1, I2, IPth basis vectors in place of omega 1, omega 2, omega p, and J1, J2, JQth basis vectors for the vector space in place of the V1, V2 up to VQ. And that will give you the components. The way in which the components transform simply follows from the way in which basis vectors and basis covectors transform under a coordinate transformation. So rather than becoming an independent statement, they just become a result which follows naturally from the definition of a tensor as a multilinear map. In particular, a 0, 2 tensor T would actually take in two vectors A and B and produce a real number. Now, if instead of giving T two vectors, you had given a single vector A in the first slot and left the second input slot empty, this actually would be waiting for a vector which, once given, will be converted into a number. So this quantity is essentially something which takes in a vector and produces a number. So if you fill up one of the two slots of a 0, 2 tensor with a vector, the resulting thing really is a multilinear, or strictly speaking linear map, which acts on a single vector to produce a number. So this would be a covector. And of course, this covector would depend on which precise vector A you fitted into the first slot. So it will be something which depends on A. So let's call this TA or something. So this is a covector TA which eats up a vector B and produces a number, and the rule for that is simple. This number is nothing but T acting on the arguments A and B. It's very easy to check that this is actually a linear map acting on the covector space. In fact, we have already done that in the last lecture. In the last lecture, we looked at a very special case of this, where instead of taking any arbitrary 0, 2 tensor, we had taken the metric tensor. Remember, the metric tensor is somewhat special in the sense that when you feed it two vectors, the resulting thing is a number, but it's not just any number, it's the inner product or the scalar product of A and B. And so you can calculate the inner product of A and B by using the metric tensor G and feeding it A and B as inputs. Or you could take this object where one of the slots of G has been filled up with A, call it, let's say, phi of A, and phi of A is of course a covector, just as before, but its action on B produces a special number, not just any number, it produces the inner product of the vector A with B. So phi A acting on B is the inner product of A and B, and in that sense phi A is a special covector, it's a covector corresponding to the vector A in this particular sense. Instead of using the vector A and the metric to produce an inner product, you could just use the covector A acting directly on a vector to produce the same result. And this is exactly what we meant when we said that you have a covector version of a given vector. A vector, of course, in the traditional notation is written with an upper index, and this quantity essentially is represented by this object. So this is basically a lower index version or a covector version of the vector A. Note that if you were to feed a vector A into the first slot of any 0, 2 tensor, you would end up with a covector. But that covector will not usually have a very special connotation. Here, if you feed the vector A into the first slot or the second slot, G being symmetric, it doesn't matter which slot is it that you fit your A in, you will get a very special covector, a covector whose job is to return, when acting on a vector, nothing but the inner product of A with that vector. Specifically, this particular covector is called the covector corresponding to the vector A, and when you write it in components, you just use the same symbol, you just use a lower index as opposed to the upper index which you use for the vector. And this is exactly what we meant when we said Gij's lower indices. And just by the same token, the inverse of G raises indices. One important thing is, if you were to feed instead of A, say C1, A1 plus C2A2, where A1 and A2 are two different vectors and C1, C2 are two numbers in this fashion. That is, you leave the second slot empty, so you're really producing a covector out of this linear combination vector. It is very easy to say that the resulting covector is exactly the same as C1T A1 with one slot empty plus C2T A2 with the other slot empty. So this business of feeding one vector into a slot of a 0, 2 tensor actually produces a covector out of a vector in a linear fashion. This is going to be a very, very important point. A tensor can be thought of, as we said a while ago, as something which produces a number out of a bunch of vectors and covectors. But if you just turn it around a bit, you can also think of a tensor as a machine. In particular, you can think of a 0, 2 tensor as a machine which eats a vector and churns out a covector. In fact, if instead of a 0, 2 tensor, you had a 1, 1 tensor, let's call that Q, let's say, it would actually eat a covector and a vector and produce a number. That's the way a 1, 1 tensor is supposed to work. But let's just say we keep the first slot empty, that is waiting for something, and feed the second slot a vector, A. So what kind of an object would this be? This would be an object which is waiting for a covector, and once it gets a covector, it's going to convert it into a number. Not only that, it's going to convert it into a number in a linear fashion. So this is a linear map which maps a covector into a number, and as we have seen already, that is nothing but a vector. So this object is actually a vector. And so you can think of a 1, 1 tensor as a machine which takes in a vector and produces another vector. And not only that, it does so in a linear fashion, as you can easily check that if instead of A, if you put in C1 A1 plus C2 A2, the resulting vector will be a linear combination of what you would get with A1 alone or with A2 alone. So a 1, 1 mixed tensor is nothing but a machine which takes in a covector and a vector and produces a number in a multilinear fashion. But at the same time, you can also think of it as a machine which takes in a vector and produces another vector linearly. Now, this particular aspect is very, very important in physics, because in physics, we very often see situations where one vector depends on another vector linearly. The most obvious example of that is when one vector is just a multiple of another vector. That is, you get one vector by multiplying another vector by a scalar. But you can have a more general situation than that, where a vector depends on another vector linearly, and that is described by a 1, 1 tensor. In fact, this is why tensors are so important in physics. In many situations, you have vectors depending linearly on vectors, and the neatest mathematical tool that you have for describing this would be a 1, 1 tensor. We will now take a look at some examples from physics where we actually need tensors because of this particular behavior which tensors have of being able to produce vectors from vectors linearly. At the beginning, we will take a look at a simpler situation. We will talk about tensors and vectors under rotations. And as we have stressed before, for rotations, there is only one kind of tensor index. You don't have to worry about upstairs indices or downstairs indices, simply because covectors and vectors transform exactly the same way under any orthogonal transformations, including rotations. So instead of talking about 1, 1 tensors, we will just talk of rank 2 tensors under rotation. Let me ask you to cast your mind back to the time when, as a physics student, you had heard the word tensor used in a course for the very first time. Of course, you might have seen curvature tensor in some semi-technical or popular science article, but if you're talking of a real tensor which you meet in a physics course, I'm reasonably sure that most of you will agree that it was the justly famous or infamous moment of inertia tensor. So that is usually the very first time people meet a tensor. Of course, in class 11 and 12 in high school, you learn that L is I times omega, and there it sort of seems implied that I is a number. Of course, a dimensional number, something which you multiply the angular velocity with to get L. In fact, you even get this result that I is sigma mi ri square, sum of a bunch of numbers, so of course it's a number. However, this result actually works only in a very limited sense. It works only when you are talking about an object which is planar and which is rotating in its own plane, and only for such a situation can you write the angular momentum vector as a product of a number times the angular velocity vector. In general, L is related to omega in a linear fashion. That is, if you were to replace omega by omega 1 plus omega 2, the resulting angular vector L will be replaced by L1 plus L2. That's the first step in linearity. Also, if you were to replace omega by alpha times omega, where alpha is a number, then L will become alpha times larger. So that's exactly what we mean when we say the angular momentum depends linearly on angular velocity. Of course, if angular momentum were a number times the angular velocity vector, in other words, a scalar times a vector, and this had been an ordinary scalar multiplication, the additional implication that would have been there is L is parallel to omega if I were a number. So this idea that I is just a number, or what we have been calling a scalar, would have actually forced you to accept the notion that angular velocity and angular momentum are always parallel to each other. And we know that that is not true. L is linearly dependent on omega, so these relations do hold, but this one does not hold in general. In fact, it holds only for very specific situations like a spherical object or some other objects which are called spherical tops, or works for this more generic case of a planar object rotating in its own plane. Which is why in high school you could get away with pretending that moment of inertia was really just a number, a scalar quantity, and did not have to worry about the fact that it was actually a tensorial object. Indeed, you had never perhaps heard of a tensor in your high school. A more complicated, detailed calculation that you do once you get to a more advanced course tells you that the three components L1, L2, L3 of the angular momentum are related to omega 1, omega 2, omega 3 components of the angular velocity linearly, but in a more general fashion than L equal to I omega seems to suggest, at least with a scalar I. What you really have is something which looks like this. L2 is I21 omega 1 plus I22 omega 2 plus I23 omega 3. L3 is I31 omega 1 plus I32 omega 2 plus I33 omega 3, where I am using 1, 2, 3 for x, y, z components respectively. And this bunch of 9 numbers, I11, I12, I13, etc., this bunch taken together can either be thought of as a matrix which is acting on the column vector formed by omega 1, omega 2, omega 3 to give you the new column vector with elements L1, L2, L3. Or you can think of these 9 numbers as components of a 2-indexed object which turns out to be a tensor of rank 2. We will now explore why this quantity has to be a tensor of rank 2. But before we do that, let me just remind you of a few more properties which this bunch of 9 numbers have. It turns out that I12 is the same as I21, I31 and I13 are the same, and so on. So, as far as the matrix is concerned, this matrix made out of these 9 numbers is actually a symmetric matrix. So it has only 6 independent components. The 3 diagonal components are independent, and if you give me any of the 3 numbers either from the top triangle or the bottom triangle, the other 3 automatically follow. So we have 6 independent components for this object. It's not just a tensor of rank 2, it's a symmetric tensor of rank 2. So we still have the relation L equals I omega. The only difference now is omega is a column vector, so is L, and I can be represented by a 3 by 3 matrix, not a single number. Now what does this tell us about the way in which the numbers I11, I12, etc. transform when you change your coordinate system? Remember, when you change your coordinate system, with x going over to x prime equals rx, where r of course is the rotation matrix, the angular momentum and the angular velocity, both being vectors, would transform to L prime equals RL, and omega will go over to omega prime equals R omega. So what does this tell us about I, the moment of inertia? Of course, you want the moment of inertia in the new coordinate frame to be simply a matrix, or represented by a matrix, which will give you this relation. That is, L equals I omega will still be valid in the new frame. It's just that the values which you use for L, the numbers which you use for L and omega, they have changed because of coordinate transformation properties. And the numbers which you use for I would also have to change. Now, if L prime equals I prime omega prime, that really tells you that R times L, where R is the rotation matrix of course, is I prime times R omega, and this has to be true for all omega, and thus what you end up with is R times I omega. Remember, L here is I omega, so R times I omega is I prime R omega. Since this has to be true for all omega, you must have this result, that Ri is I prime R. And so the new value for the moment of inertia tensor written in this matrix form is simply I prime is Ri R inverse. So under a coordinate transformation, what happens to a moment of inertia matrix is that it undergoes a similarity transformation. Now that's great, because in linear algebra we have learned many properties of the similarity transformation, and that's a very useful tool to use. Now, written in terms of the components, all this tells us is that the ijth element of I prime is sum over k and L of Rik, I, kl, R inverse, Lj. And of course, we would usually not write the sum over k and L because we are using the Einstein summation convention, where repeated indices are summed over. And although I have said over and over again that in order to be summed over, one of the pair of indices has to be downstairs, the other one has to be upstairs, but that is for a general linear transformation. For orthogonal transformations, it doesn't matter because there are only downstairs indices. Repeated indices are summed over. Now, just to remind you, R inverse is the same as R transpose, R being orthogonal. So R inverse's Ljth element is actually R's JLth element. As a result, this equation simply becomes Rik, Rjl, Ikl, which is exactly the way in which a second rank tensor, or rather the components of a second rank tensor, transform when you carry out a coordinate transformation. I would urge you to go beyond the restriction of this orthogonal transformation and check for yourselves that, strictly speaking, this I should really be a 1, 1 tensor in the general case. That should be sort of obvious from the fact that it has an R inverse in the transformation rule for it. But please work it out yourselves. Of course, since we are talking about rotations and rotations only, it doesn't really matter. You have only one kind of second rank tensor. Now, while we are at this, let me point out two very important things. As I've said before, what does the relationship L equal to I omega really mean? Or rather, what does it mean in general when you say one vector is related to another vector via multiplication by a tensor? It simply means that the two vectors are linearly related but are not in the same direction in general. And that is the most important feature of a tensor as opposed to a scalar multiplying a vector, giving you another vector. Of course, if a scalar were to multiply a vector, you would get a new vector, and this new vector would depend linearly on the original one as well. It's just that a tensor multiplying a vector does the same thing but in a much more general fashion. A scalar multiplying a vector forces the resultant vector to be in the same direction as the original vector. Here, that is no longer a demand. L may or may not be in the same direction as omega. Although it is true in general that L equal to I omega with a tensorial I implies that L and omega does not have to be in the same direction, there are special situations where L and omega do happen to be in the same direction. And in order to understand that, let me go back to the transformation rule for I prime in terms of I written in the matrix language. Remember, as far as matrix version is concerned, I is simply a 3 by 3 matrix. And under the coordinate transformation, x prime equals rx, that is x goes to x prime equals rx, I goes to I prime, which is a similarity transformation as we had just seen. Now, the beautiful thing about similarity transformations is that you can actually use the similarity transformation to make the resultant equivalent matrix much, much simpler. In particular, if the matrix is diagonalizable, we should be able to find a transformation which makes it into a diagonal matrix. Now, the important point that we learn from linear algebra is that a symmetric matrix is always diagonalizable. And not only that, not only is it diagonalizable, it's actually orthogonally diagonalizable. What that means is that you should be able to carry out an orthogonal transformation which diagonalizes it. Now that's great because after all we are talking of rotations which are orthogonal transformations, and what this piece of linear algebra knowledge guarantees to us is that we will be able to find a particular rotation which is going to make the resulting I diagonal. So for a special choice of R, which of course means you are changing your coordinate system in a special manner, the resulting moment of inertia tensor will end up having this particular form, with 3 non-zero values along the 3 diagonal components, but zeros everywhere else. Now, what does this tell us about the relationship between L and omega? It tells us that L1 is I1 omega 1, L2 is I2 omega 2, and L3 is I3 omega 3. Since I1, I2 and I3 are different in general, this still does not tell us that L and omega are in the same direction. After all we have done is change your coordinate system. That has not changed the underlying vectors. So, if the vectors were not in the same direction to begin with, just changing your coordinate system will not achieve that. However, what it does tell you is this. Suppose I have an angular velocity which is entirely along the y-axis. That is, omega vector has only one non-zero component which is omega 1. All the other components are 0. Now, in general, for a non-diagonal moment of inertia tensor, this would have given us a result like this. L1 would have been I11 omega 1. L2 would have been I21 omega 1 and L3 would have been I31 omega 1. And these two would in general not have been 0. What that means is, although your angular velocity had been only in the one direction or the x direction, the angular momentum would have all three components. In other words, the angular momentum would not have been in the same direction as the angular velocity. But look at the special situation where we have gone over to a new coordinate system in which you have this diagonal moment of inertia tensor and hence this set of relations between L's and omegas. Now you will get this result. L1 equals I1 omega 1 and L2 is I2 omega 2, but omega 2 is 0, so L2 is simply 0, so is L3. So now L will be parallel as a vector to the omega vector. And you can easily see that that will happen not only for an angular velocity vector which is entirely along the one axis, it will also happen if the angular velocity vector were entirely along the two axes or entirely along the three axes. So what this guarantees is that for any object whatsoever, for any rigid body whatsoever, no matter how symmetric or asymmetric it is, there always exists a choice of coordinate system or three distinct axes for which, if the angular velocity were along one of those three axes, the angular momentum would also be along those three axes. Of course, in general, because of the fact that the proportionality constants are different for the three axes, if you were to have an omega in an arbitrary direction away from the axis, L would not actually be in the same direction. L1 will be something times omega 1, L2 will be something times omega 2, L3 will be something times omega 3, but these three somethings will be different numbers in general, so you will not have L and omega in the same direction in general, but you will get three special directions along which L and omega are co-directional. Of course, if your system has special symmetries, things can be even more special than this. For example, for a sphere, no matter which direction your angular velocity is in, it is obvious that the angular momentum will always be in the same direction. What is not so obvious perhaps is that not only does this work for a sphere, it also works for other systems which have sufficient symmetry, like say an homogeneous cube or a homogeneous tetrahedron. So these things, which are very different from spheres geometrically, are actually called spherical tops in classical mechanics. And that, of course, is a huge topic in itself. There are, of course, several other examples in classical physics where you get to see a tensor in action. For example, a very familiar expression that we have in electricity and magnetism is the connection between the electric field and the displacement vector. And for an isotropic medium, the two are related to each other by just a dimensional constant called the permittivity. So this is just the permittivity of the medium, and for isotropic media this really is something which looks like a scalar. However, for an anisotropic medium, what you really have is a relation which goes like this. Even when the electric field is weak enough that we can consider the relationship between E and D to be linear, what you have is a relation which goes like this. The similarity between this one and the relationship between angular momentum and angular velocity is not accidental. They are basically the same kind of objects at play here. D and E are vectors, and this epsilon, which now has 9 components, is really a second rank tensor. Once again, on purely physical grounds, you can show that this is the symmetric second rank tensor, and so by carrying out an appropriate similarity transformation, in particular a rotation of coordinates, you should be able to go to a situation where the epsilon tensor becomes diagonal. So you end up with only the principal permittivities along the diagonal, epsilon 1, epsilon 2 and epsilon 3. All the other numbers will be 0 for a special choice of coordinates called the principal axis system. Now, I don't really want to repeat all I said about the relationship between angular velocity and angular momentum, but the basic principle stays the same here. Once again, in a linear approximation, the relationship between angular momentum and angular velocity is actually linear. However, the relationship between d and e is linear only as a first approximation, where we are dealing with electric fields which are not immensely large. If you're talking of, say, electric fields caused by highly directed laser light, this relationship would fail and you would have to worry about higher power terms which have products E1, E2 or E square, or even third order or higher order terms. But for most situations, the electric field is weak enough that this approximation of stopping at a linear term is quite decent. And there, what you end up with is this relationship that d and e are related to each other by d equals epsilon e, of course, but epsilon now is no longer a permittivity scalar, it's actually a permittivity tensor. And this permittivity tensor, of course, takes its diagonal form when you are using a special set of axes called principal axis. And for an isotropic medium, what happens is that it's still really a tensor, but it's a tensor in which is not only diagonal, it has equal numbers along the diagonal. All the three permittivities, epsilon 1, epsilon 2 and epsilon 3 are actually the same. And so what you end up with is a permittivity tensor which is essentially epsilon times the identity matrix. So it's effectively the same thing as a number epsilon. So it's in the isotropic limit that this relationship between d and e becomes a multiplication by a scalar effective. So although it's always really a tensor multiplying e, we can get away without worrying about the tensor nature of epsilon as long as we are dealing with isotropic media. Now, the moment of inertia tensor or the permittivity tensor are by no means the only tensorial objects which are of interest to a physicist. I am pretty sure that many of you who are listening to this series of lectures are interested in tensors primarily because of their applications in general relativity, or perhaps special relativity. In fact, what you see on the screen right now is a sort of teaser for the things that we are going to describe in later lectures. For the time being, just take them as some symbols scribbled on the screen. We are going to explain what this means, what this has got to do with curvature and non-Euclidean geometries later. But as you all know, non-Euclidean geometries are an important tool in physics, especially when we talk about general relativity. However, in today's lecture, we are not going to go there. We are going to stick to Newtonian physics today, and I'm going to point out that there is a branch of Newtonian physics which deals with tensors to a much greater extent than general relativity does. And that happens to be the subject of elasticity. Just think about it a bit. You have stress. Now, we think of stress as force per unit area. But what this really says is that the force acting on a small element, area element in a material is actually linearly dependent on the area element. So if I write the area vector as A and the force acting on it as F, what you can write is F is sigma A. But this sigma, the stress, is not really just a scalar. If it had been, then the force would always be forced to be along the area vector. Remember, by convention, the area vector is normal to the area. And if this were the real relationship, then we would always be forced to consider forces on area segments which are always normal to them. That is, shear forces which are not directed towards the area vector, could not be treated by this. But they are really important things, especially when we talk about the behavior of solids. And so what you really have is a relationship between the area vector and the force vector, which is linear, but which is not necessarily multiplication by a scalar. So stress is really not a scalar. is a second rank tensor. Strain actually relates one vector, the deformation displaced vector, to a position vector. So that also is a second rank tensor. So strain and stress are both examples of second rank tensors. Now the quantity which connects them, the elastic moduli, what are they really? They are ways actually take in strain as an input and converts that to stress. Of course, we have seen special cases of that. You take linear strain, longitudinal strain along the length of a wire, connect that to the stress, you get what is called Young's modulus and so on. But if you want to take a look at the whole thing in one go, what you need is a machine which will take in a second rank tensor, the strain, and spew out a second rank tensor, the stress. So elasticity has to be described actually by a fourth rank tensor, a tensor with 4 indices, of which 2 will be contracted with the strain, that will leave you with 2 indices which will describe the stress tensor. In fact, if you go deeper into the theory, you will find higher and higher rank tensors becoming more and more important. I just wanted to inform you that there are other, perhaps seemingly more mundane branches of physics where you use tensors in a big way. General relativity is not the only place where it is used. At this stage, many of you may have a legitimate complaint. This series of lectures was called Tensor Analysis. So far we have talked about vectors and then generalized to tensors. We have talked about their definition, their properties. We have talked about some algebraic aspects of tensors, like how they form a linear vector space. We have also talked about examples, especially examples from Newtonian physics of tensors. However, we have hardly touched upon the issue of calculus, and without calculus, how can there be analysis? I did point out earlier that differentiation, especially differentiation of vector fields and tensor fields, is slightly subtle, for the simple reason that while you can happily add or subtract tensors at one given point in space or space-time, as the case may be, adding or subtracting vectors at different points in space will not lead to new tensors, simply because tensors at different space points transform differently in general. We will talk about differentiation of tensors soon, and that will help us get the necessary mathematical tools for general relativity. But before we go there, in the next lecture we are going to talk a bit more about the application of vectors, covectors and tensors and these kinds of objects in special relativity. This will serve as a warm-up for our study of general relativistic topics. But let me point out that the use of tensorial methods in special relativity is of great importance in its own right. Let me warn you at the outset though, that this is not going to be a special relativity course. That of course is a different ballgame altogether. We are just going to discuss some of the mathematical tools that you will need to do advanced special relativity. For actual details on the subject, you should definitely consult textbooks or other courses. Till the next lecture then, goodbye.